Hey everyone, this is Dr. Anna, and today we are going to start a new module, the plate tectonics. We already learned plate tectonics in physical geology, so I mostly just try to give you added information at the same time and go through what we already have learned. I hope you remember that we have three main plate tectonic environments, the extensional, the compressional, and the transform, and I'm going through each of them a little bit. We are going to start with the extensional environment, which is the first type. This happens along divergent plate boundaries. The most common fault along this kind of plate boundaries are normal faults. I will use a block diagram so you understand what happens here. As you can see, here is the fault plane. Oops, that's so cool. I can zoom in. So this here is the fault plane. This is the fault line. The block below the fault line is the footwall block. The one above the fault line is the hanging wall block. If we want to see what happens if it's a relative lengthening or shortening, we have to follow a layer on both sides. So if you look at the brown layer, it's right here on this side. And as you can see, because the footwall moved down, it's right here on this side. I have to change the color really quick so you can see it better. Purple. You can see that the brown layer finishes on the footwall side right here, but it finishes on the hanging wall side right here. So this brown layer is missing in between these two lines. So that missing layer is the relative lengthening. So this here is the relative lengthening. I have an example for this right here on the next slide. As you can see, this is a normal fault, and I'm going to show you the important parts. That's the fault line. This here above the fault line is the hanging wall. How do we call the one below the fault line? Yes, right. It's the footwall. Footwall. Okay, we have the person for scale. And we're gonna check out what happens with the layers. You can see that the hanging wall is moving down. Check on this white layer on both sides. You can see that the white layer is missing in between these 2 points right here. So that is the relative lengthening. So that's the relative lengthening. Wherever that layer is missing, that is how much longer the area become because of the divergent, the pulling apart situation here. Now this here shows you the Graben fault. I hope you remember the Graben fault. Graben fault is when you have two facing each other normal fault. And I have a really good example right here. So I'm going to show it really quick. This here is the fault line for this side. And this is the footwall, and this is hanging wall. Now, for this fault line, if you look, this here is the footwall, and above the fault line is the hanging wall. So a hanging wall is same for both. Where is the missing layer? You can see it's right here. So that's the relative lengthening here, relative lengthening here. So it's two typical normal fall, and they are facing each other. So you can see that the middle here is fall in. So this is what we call Graben fall. Now here it's a typical rift basin, and you can see that what happens along rift basins is that you have facing each other normal faults, and the middle part is falling in. Okay, so this is what we call Graben fault, and usually they are producing narrow deep basins. I have another really good example, probably more. This here is a typical facing each other normal fault right here. So it's one fault, and this happens at the Inyo White Mountains in Owens Valley. It's the Sierra Nevada, so it's in California. I have another one, and this here is the Graben fault at that valley. This is one fault. This is the other fault line. You see, the one below the fault is the footwall. One above the fault is the hanging wall. And like every single Graben fault, the one before below is the footwall, and the one above is the hanging wall. So this here is the hanging wall for both, and we can see that this here is the missing, the relative lengthening, and here this is the relative lengthening. So both sides you can see the relative lengthening, which is a result of the divergent plate boundary. Second type is the compressional stress or compressional environment, and this is what happens along convergent plate boundary. Here we have most commonly the reverse fault. So this here shows a reverse fault right there. That's the fault line. Below the fault line is the footwall. Above the fault line is the hanging wall. And what can you see here is the forces are going toward each other, So it's a big compressional stress, basically. And we can see that the brown layer, which we're going to pick up here again, the brown layer is actually being repeated over each other. See, this side and this side is the same layer, and this is what we call the relative shortening. There is an example here. This is the fault line right here. Below the fault line is the foot wall. Above the fault line is the hanging wall, and we can pick this white layer right here, which is over here. So you can see that there is a overlap in between this area, and that's the shortening, shortening. Okay, so it's a typical reverse fault. This is a special reverse fault. We call it thrust fault. It's very, very common along convergent plate boundaries. Around us in the Blue Ridge Mountain and the Valley and Ridges area, there is a lot of thrust fault. If you were one of those who went to Dixie Cavern with me, there was the Salem fault, which we could see inside the cavern. If you didn't go with me, but the tour guides, they point this out. So it's a typical thrust fault. When that happens, that means that the angle of the fault is very, very low. This is the angle of the fault. So it's less than 45 degrees. It's very low angle fault. This case, as you can see, the shortening is much bigger than in the other case, where the angle is steeper. When you have a thrust fault, the relative shortening is much more extensive. Sometimes when it's really, really low, like it could be close to like 0 or 1 degree, that just means the hanging wall block can go really far away. This is the hanging wall, by the way, and this is the foot wall. So the hanging wall can really go far, far away. Like myself, during my PhD study, I worked in Hungary, and my study area was the same rock as was about 500 miles away in the Alps. So the hanging wall moved that far away from the foot wall. So the thrust fault is a special reverse fault where the hanging wall can move really far away because the angle of the fault is very, very low. Okay, so that's a typical thrust fault here. They already drew everything here. This is the thrust fault itself, and that's the overhang. This is another one. You can see this here is the fault line, and that's the hanging wall, foot wall. And you can see it's a very, very low angle relative to the horizontal. This block just moved over. The third setting is the transform, and that's along the transform plate boundary. Here we don't have any kind of vertical movement, only horizontal. And the fault movement has taken place in a horizontal direction. Remember, this happens along mid-oceanic ridges because you cannot put a straight line on a sphere. So therefore, it has to have these low transform faults along it. So you can see right here, this is one block and the other one, and this block is moving this way and the other block is moving the other way. We can have left lateral. If you're standing here and looking at which way the other block is going, you can see it's going to the left. But if you stand here, then you can see it's still, if you look at this block, that it's still moving to the left. And when it's right lateral, you're standing on this block, and you can see that that block is going to the right. And opposite to, if you're standing in this one, then it's still going to the right. Basically, you will see this along transform plate boundaries. I can show you this amazing one. Right here is the fault line. See? That's the fault line. And if we're standing on this block, which way did the fence move? See, that's the fence. You can see the fence move to the right. But if we stand on this block, then you can see that it's still a right laterals, because if you're looking this way, then this block went to the right. So it's a right lateral strike lip fault. After this introduction, I want us to turn our focus to the plate tectonics itself. First, I want to show you two videos which was made by the IRIS, which is a very famous geologic organization which is spreading the science, and it's part of the NSF, the National Science Foundation.
The cool, rigid outer layer of the Earth, the lithosphere, is broken into massive plates. There are about a dozen major plates and many smaller plates in continuous motion as they collide with, slide under, or move past each other in a process known as plate tectonics. A plate may be entirely oceanic lithosphere, like the Pacific Plate, or, like the North American Plate, can be part oceanic and part continental lithosphere. We will return to lithosphere types in a minute, but first, let's look inside the Earth to clarify the layers. The mantle is a 2,900 kilometer thick, high magnesium silicate rock layer located between the crust and the core. The uppermost part, the lithospheric mantle, is cooler and more rigid than the deeper mantle. It lies above a hotter and more ductile layer of similar composition called the asthenosphere. As an analogy to how rock can either be brittle or ductile, consider a taffy bar like the Big Hunk. When force is applied, they are brittle when cold and ductile when warm. Zooming in to a tectonic cross-section, we see that the lithospheric plates are composed of crust on top of the outermost rigid part of the mantle. Although the mantle has a different composition and higher density than the crust, these two layers migrate as a single mechanical layer called a lithosphere or tectonic plate. This is where earthquakes occur as the brittle rock that makes up the plates fractures and breaks. The hotter, more ductile asthenospheric rock does not fracture to produce earthquakes. Continental lithosphere, with continental crust above lithospheric mantle, typically ranges from 150 to 200 kilometers thick. Continental crust stands above sea level because it has an average thickness of 40 kilometers and is mostly made of more buoyant, silica-rich, low-density granitic, sedimentary, and metamorphic rocks, which form the continents. Oceanic lithosphere, formed at spreading ridges, is typically 50 to 140 kilometers thick. Oceanic crust is only around 8 kilometers thick and is denser than continental crust because it contains less low-density silica and more high-density iron and magnesium. Thus, it forms the ocean floor with its top surface below sea level. Relative motion between plates can be broadly grouped into three main categories: transform, divergent, and convergent.
The next thing which will be really important to learn about is the driving forces behind the plate tectonics. But I'm going to finish this segment right here and continue in the next segment. I will see you there, guys.